So hello everyone, today we will solve a set of exercises on the last two chapters. So we'll start with exercise 1. Consider the following polynomials f of x equal 5x power 4 plus 3x power 3 plus 1 in z7 of x and g of x equal 3x power 2 plus 2x plus 1 also in z7x. We need to find the q of x and r of x, the quotient and the remainder that we talked about in the division algorithm. Okay, so we need to find the unique p and the q polynomials so that f of x is equal to p of x, g of x plus r of x, where r of x is equal to 0 or its degree is strictly less than the degree of g of x. How to perform this? Most of us did this Euclidean or division algorithm in high school, where the polynomials were in r of x, not in z7 of x. Okay, so most of us did this work in r of x, not in z7. We will do this work now in z7 of x. So this is a kind of refreshing or revision of something seen before. 5x power 4, here we put g of x, 3x power 2 plus 2x plus 1. Here we put f of x, which is 5x power 4 plus 3x power 3 plus 1. Take the term of highest degree here on the left, divided by the term of the highest degree here on the right. You find that 5x power 4 over 3x power 2 is equal to 5 times the 3 inverse x power 2. 3 inverse in z7 is 5 also, since 3 times 5 is equal to 15, which is congruent to 1 modulo 7. So the inverse of 3 in z7 is 5. 3 inverse is 5. Then here we have 5 times 5. 5 times 5 is equal to 25, which is congruent to 4 modulo 7. 4 modulo 7. So this term here is equal to 4x power 2. Now minus here, then multiply 4x power 2 by 12x power 2 is congruent to 5x power 4. 4 times 2 is congruent to 1, which is 8 and congruent to 1. So we have 1x power 3. 4x power 2 times 1 is 4x power 2. This cancels out with this term here. 3x power 3 minus x power 3 is 2x power 3. Minus 4x squared minus 4 is equal to 7 minus 4 equal to 3. So we'll put here 3x power 2 plus 1. Now repeat the process in the first step. 2x power 3 over 3x power 2 is equal to what? So 2x power 3 over 3x power 2 is equal to 2 times 5, 7, 7 congruent to 3, 3 modulo 3, 3x. Okay, so here we have 3x. Now multiply 3x by 3x power 2 is 9x power 3. 9 is congruent to 2, so we put here minus 2x power 3 plus 6x square plus 3x. Now this term cancels with this term. 3x power 2 minus 6x power 2 is equal to minus 3x power 2, which is 4x power 2, which is congruent to 4. Minus 3 is congruent to 4, so we have here 4x power 2. 1 minus 3x minus 3x minus 3 is equal to 7 minus 3, which is congruent to 4. Okay, so plus 4x. Now plus 1. Repeat the process again. 4x power 2 over 3x power 2 is equal to 4 times 3 power minus 1, which is equal to 4 times 5, 20. 20 is congruent to 6 modulo 7. So here we have plus 6. 6 times 3 is congruent to is equal to 18, which is congruent to 4 modulo 8, so minus 4x power 2. 6 times 2, 12. 12 is congruent to 5, so here we have plus 5x. 6 times 1 is 6. Now this term cancels with this term. 4 minus 5 is equal to minus 1. Minus 1 is congruent to 7 minus 1, which is congruent to 6 in mod 7. 1 minus 6 is minus 5. Minus 5 is congruent to 7 minus 5, which is congruent to 2 modulo 7. So plus 2. This is the remainder r of x. Here the degree is 2. Is 1. Strictly less than the degree of g of x, which is 2. And this is the quotient q of x. You can check whether if q of x, you can multiply qx by g of x and add r of x, you will get definitely f of x. So this is exercise 1. Exercise 2, claim I'll show that this ideal is maximal in q of x. Remember that q is a field, and if f is a field, then f of x is a principal ideal domain, which implies that qx is a principal ideal domain. So in a principal ideal domain, an ideal generated by a polynomial q of x is maximal if and only if q of x is irreducible over the field, which is here q is irreducible over q. Now definitely x, the polynomial q of x equal x is irreducible over q. We cannot write x as a product of non-unit polynomials, non-constant polynomials of lesser degrees. So p of x equal x is irreducible over q, and so this concludes the result. We can say that the q of x quotient by x also is a field. Now exercise 3. Study the irreducibility. First part A, we have p of x equal x power 4 minus 5x power 3 plus 3x minus 2 in qx. By rational root test, you can check rational root test in the reference I mentioned. We have p of x has only possible roots in q 2 and minus 2. So the possible roots of p of x in q are plus 2 and minus 2. Let's check. P of plus 2 after calculation is equal to minus 20, different from 0. P of minus 2 is equal to 48, which is different than 0. So then P of x has no roots. Then P of x has no roots in Q of x. So by rational root test or rational root theorem, P of x has possible roots plus 2 and minus 2 in Q. We calculated P2 and P minus 2, both different from 0. Then P of x has no roots in Q of x. So P of x has no linear factors in Q. If P of x is reducible over Q, then must be reducible over Z. That's Gauss's lemma. That's Gauss's lemma. We talked about it. So P of x, if P of x is irreducible over Q, then P of x can be reduced into, or can be written as product of 2 by 2, of two polynomials, each of degree 2 and z of x. So can be written as x power 2 plus ax plus b into x squared plus cx plus d. This implies that P of x is equal to x power 4 plus cx power 3 plus dx squared plus ax power 3 plus acx, just x squared, just expand and compare the left and the right hand side, plus adx plus bx squared plus bcx plus bd. By comparison, we get that a plus c is equal to minus 5, a plus c is equal to minus 5, ac plus b plus d is equal to 0, bc plus ad is equal to 3, bd is equal to minus 2. Remember, a, b, c, d are all in z. Now, the possible solutions for the last equation here, is, or are, b equal 1, first case, so first case, b equal 1, and d equal minus 2. In this case, we got a plus c equal minus 5, ac equal 1, minus 2a plus c equal 3. This implies that a is equal to minus 8 over 3 does not belong to z. Second case, so this case is impossible. Second case, b equal minus 2 and d equal 1. This case implies the following system: a plus c is equal to minus 5, ac is equal to 1, a minus 2c is equal to 3, and so c is equal to minus 8 over 3 does not belong to z, and this case was also impossible. Similarly, we get impossible cases, impossible values or cases for d equal to minus 1 and d equal to, and for d equal 2 and d equal minus 1. So in these all 4 cases, we got impossible results, so we cannot find a, b, c, d. So we cannot find that q that p of x is irreducible over z, and so p of x is irreducible over z, implying that p of x is irreducible over q. Definitely, p of x is irreducible over q. Part B, the polynomial p of x is equal to x power 2 plus 2x plus 2 belong to z3x. Now this polynomial is of degree 2, so if this polynomial does not have any root in z3 of x, then this polynomial is irreducible. Okay, so if a polynomial is of degree 2 or 3, then it's irreducible over a field, of course, if and only if. So it's reducible over a field f if and only if it's the polynomial have a root in the field. Okay, so let's check. Since Z3 is a finite field, so we can check P of 0, P of 1, P of 2. That's not a lot of calculation. So P of 0 is equal to 0 power 2 plus 2 times 0 plus 2, it's equal to 2. Not congruent to 0 modulo 3, of course. Similarly, P of 1 is congruent to 2, not congruent to 0 modulo 3. And P of 2 is equal to 10, which is congruent to 1 modulo 3, not congruent to 0 modulo 3. So this polynomial, and this polynomial, as we mentioned, is of degree 2 with no roots in Z3, then this polynomial P of x is irreducible over Z3. Okay, final example, P of x equal 5x power 3, sorry, 5x power 5 minus 6x power 4 minus 3x squared plus 9x minus 15 in q of x. Okay, p of x also in z of x. So taking p equal 3, a prime number, as you see, p divides minus 15, p divides 9, p divides the whole coefficients except the leading coefficient, p divides minus 3, p divides minus 6, p does not divide 5, and p squared does not divide, doesn't divide minus 15. So this polynomial is irreducible over q by Eisenstein's criteria. Exercise 4. Claim or show that three is irreducible in Zi, but 2 and 5 are not, so they are reducible. Okay. Proof. Suppose that 3 is equal to x dot y. Okay, let n be the following mapping on Zi. Be defined by n of x equal to a power 2 plus b power 2. Okay, we can check that n is an Euclidean valuation on the Gaussian ring Zi. So, and holding the following properties: n of x equal to 1, you can check n of x equal to 1 if and only if x is a unit. N of x y is equal to nx times ny. Okay, so this Euclidean valuation has the following properties. Now, we claim that 3 is equal to x dot y. We need to find that either x or y is a unit. So either nx equal to 1 or ny equal to 1. Now, n3 is equal to nx y. Using the following property here, we find that n3 is equal to nx times n1. Now, n3, following the definition of n, is equal to 9. So 9 equal nx, n1. This implies that nx divides 9, so nx belongs to 1, 3, 9. If nx equal to 1, nothing to show. X is a unit, and then 3 is irreducible. So if nx equal to 1, nothing to show. If nx equal to 9, then ny is equal to 1. So 1 times 9 is equal to 9. And again, nothing. This implies that x is irreducible. Now, this left us with the case where n of x equal to 3. If nx equal to 3, suppose that x is equal to a plus bi in Zi. If nx equal to 3, then we can find two integers a and b, so that a square plus b square is equal to what? Equal to 3. And this is impossible in Z. You cannot find two integers, a couple of integers with the squares, with sum of squares equal to 3. This implies that 3 is irreducible. So nx cannot equal to 3, nx equal 1 or 9, and in both cases x, this implies that 3 is irreducible in Zi. Now, what about 2 and 5? Look, 1 minus I into 1 plus I is equal to what? 1 square plus or minus I square, which is equal to 1 minus minus 1 equal to 2. So 2 can be written as 1 minus I into 1 plus I. 1 minus I is irreducible and not a unit. Here, this is irreducible and not a unit. And so 2 is not irreducible, so reducible over Z can be written as a product of non-units. You can check that these are non-units simply by calculating n of 1 plus I is equal to 2, n of 1 minus I also is equal to 2. So 1 minus I and 1 plus I are non-units, and 2 is a product of non-units in X. and zi, sorry, and 2 is irreducible. Similarly, for 5, we can write, or one can write 2 minus I into 2 plus I equal to 2 square minus I square, which is equal to 5. 2 minus I is non-unit, 2 plus I is non-unit, and 5 can be written as product of non-units in zi, which implies that 5 is reducible as well as 2. Exercise 6, 5. Show that z minus 6 z of root minus 6, which is equal to what? A plus b radical minus 6, where a and b belong to z, is not a unique factorization domain. Solution is very simple and short. You can write 10 as 2 times 5, and you can write 10 as 2 minus root minus 6, 2 plus root minus 6. These are two different factorizations of 10 in z radical minus 6 or root minus 6. So z of root minus 6 is not a unique factorization domain, and of course 2 is not equal to any of these factors up a multiplication by unit, any of these factors up to a multiplication by units. So this concludes the result. Now in the next video, we will start with a new chapter on fields. We will talk about the fundamental theorem of fields, about splitting fields, about algebraic closure, about monic polynomials, about transcendental elements, algebraic numbers, and so on. So see you in the next video. Bye bye.